exactly this. Got it. I hope everyone is listening online, by the way. So, okay, so you have got it. Got it. Okay. So we have this very simple description that is actually very convenient in the sense that when we combine that with hydrostatic equilibrium, leads to the very well-known result that objects made of pure hydrogen that are not stars, don't have internal sources of energy, have a radius that is independent of mass. Now, what happens with Saturn and Jupiter, the two gas giant planets we have in the solar system? Saturn is obviously smaller in radius compared to Jupiter by 80% of the radius of Jupiter. And in terms of mass, it's less massive. Now, the difference in radius is not due to the mass itself. It is due to the abundance of the heavy stuff in relation to the total mass. And by heavy stuff, I mean core material and a little bit of that heavy stuff also mixed in the envelope, but most of it is in the core. So this already tells us that gas giant planets, without any geophysical observation, only knowing general properties of hydrogen and the radius of a planet, they have heavy stuff other than helium. Okay. Now, but what about the distribution of that heavy stuff? We think it's concentrated near the center, mostly as an ideal situation in which you can form the planet with a compact core. A compact core is required to form the planet, and I will talk about that later on in terms of traditional theories of accretion of planets like this. But what about other distributions? Other distributions like the dilute core. This is an idea that has become more strong and prominent in the last decade under the scope of the missions Cassini for Saturn and Juno for Jupiter. In this scenario, you have the same amount of mass that you would put in the center. Now that mass is distributed radially and dissolved in the helium, which is a liquid. And the consequences for that is not only a distribution of mass, but the fluid changes properties. Now you have a chemical gradient that can stratify the fluid. By the way, the stratification can survive variations in temperature because the material has a very low thermal expansivity. So you can, with this material, you can make the interior stratified. With that, you change the way the planet works mechanically, interiorly, in the interior. The heat now lives differently. It's not convection. You can have double diffusive convection and other things, but certainly not overturning convection. And also, it changes the way you understand the dynamic, the creation of the magnetic field, because you have convection only in a thin layer. And mainly, maybe fundamentally, the most important thing is that you form the way you change the way you form the planet. Okay, and I will talk about that very briefly in terms of what we mean by planet formation, and particularly gas giant planets. This is, of course, a complicated field, and I will just remind a few things. When we talk about planet formation, planets like Jupiter, but also exoplanets, we see them by the thousands in the near galaxy. What we mean is this process: how do we go from a molecular cloud to a planetary system with a short period of protoplanetary disk? It's a short stage compared to the life of the planetary system. But it's important to understand how do we go from this structure of protoplanetary disk, which is gas and dust, into forming discrete structures we call planets. We see these structures, planetary disk, in the nearby galaxy, and of course, we see the planets. Now, the processes, the physics, and the models, the theories that connect these two structures are many, and the constraints are scarce. So I will only talk about the very simple ideas rather than going into the weeds of this process. This is how the planet grows in mass. It's a function of time. The time scale here, as you see, is 10 million years. It's very short compared to the age of the solar system, 5 billion years. And there are 3 different stages, and different things are happening in those stages. First of all, the process must be rather rapid. We have a nebular clock, which means that after 10 million years, the material that can go into forming a planet is gone with photoevaporation or other processes. So it needs to happen rather quickly. And then we have constraints regarding the availability of material in terms of solid material to form different stages of the planet. So the first stage, stage one, you form this core, this compact core, right? You need a structure that it is formed from the accretion of pebbles, little pebbles like in a beach but made of dust that accrete in an instability to form something that is 10 times the mass of the Earth. You need that to later gravitationally attract gas on top and form this traditional picture of the gas giant planets. And this way of thinking about forming planets is what led to the prediction of, well, gas giant planets should have compact cores without having any geophysical observation, of course. Now, the problem with this, as you see, the outcome of this is a compact core surrounded by gas. At the phase 3, where you have this exponential growth and in the accretion of gas, and you end up forming something with 100 Earth masses, which is kind of Saturn, but can be larger, even like Jupiter. So the problem with this is you don't get a dilute core like what we observe right now. But people think about maybe alternatives to this model in which you can accrete planetesimals. These are objects of hundreds of kilometers in radius that can accrete into this embryo or core. At the same time, you're accreting gas, and the resultant structure is something like this. Here in the vertical axis, you have, this is the fraction of heavy material or core material as a function of the radius in terms of masses of the Earth. So you get this compact structure, right, like a compact core, and then this phase 2 where you are creating both solid material or rocky material in the form of planetesimals and gas. This leads you to something in between the two end members I already described, something that may have an interior structure like a core that is surrounded by a stratified fluid with a dilute structure. Now, an alternative in terms of formation is a giant impact. In this scenario, we have a big object of 10 times the mass of Earth hitting Jupiter after formation. And this object has enough energy to go through the envelope, reach the core, impact the core, and pulverize the material and dissolve all the material into a diluted structure. So all I'm saying here is we have different views in which, and different ways in which we can form the planets. It's not clear exactly which one of those is true, and all of them have different problems. So this highlights the need for knowing exactly, well, is there a dilute core or a compact core? Do we need all this storage to form the planets? And not only whether there is an extended dilute core, but also how extended it is. Is it reaching 0.5% of the radius? Is farther out? All those things are relevant to the way we assemble the planets. And I will be providing more details as we talk about that. Now, how do we can do this? Well, we do this frequently on Earth. We can think about, for example, normal modes. Planets oscillate with frequencies that are intimately connected to the interior structure. So if we know those frequencies and we know them for the Earth, we have a handle on what is below. We can run, forward modeling and try to match those frequencies. Unfortunately, for Jupiter, this is much harder than done for Earth. It's not only far, there's no surface to install seismic network, but we have alternatives, like in the case of Saturn, ring seismology. It's been hypothesized decades ago that the rings can work as a seismometer, and recently has been proved true. What I'm showing you here are different normal modes for Saturn as a function of the position in the Z ring, this ring right here. And this is just the azimuthal degree of the normal mode. The way this works is that the planet oscillates, and these oscillations actually move a lot of mass, and they create a gravity field that has a time dependence. Now that gravity field resonates with the mass that orbits Jupiter in these rings. These are tiny objects of ice, and you create waves that travel along the rings, and those waves can be observed with photometry, like the camera on board of Cassini. So many of these modes have been detected, and not only that, they have been used to create interior models. The important quantity actually is this Z, again, this abundance of heavy stuff, it's a function of radius, and the Brun-Weisel frequency also is a function of radius. So what do we see on Saturn is an abundance of material that may or may not have a compact core at the center. There's uncertainty. These are multiple models fitting the data and different degrees of likelihood. And the important feature is really this gradient and the abundance of heavy elements as a function of radius. That is certainly not a compact structure. There's no discrete structure in the interior. There is a smooth change from 100% of rocky material that transitions into hydrogen with a different composition of heavy stuff. Now, this naturally leads to a Brumbach's frequency that is different from zero. This is Brumbach's frequency. We use this in oceanography, of course. And this just indicates the level of stratification of the fluid. The density is not that relevant, but just shown there for because we can retrieve it. Okay. Now we cannot use this on Jupiter. So how do we go about learning about the interior of Jupiter? Well, the alternative is gravity directly from a spacecraft. What I'm showing you here is the Juno spacecraft that has been orbiting Jupiter since 2016 in multiple orbits. And the way we collect and retrieve data from the planet is from tracking the motions of a spacecraft. Like you can think about the ideal case in which the planet is a point mass source. In that case, we can know very well the trajectory of a spacecraft just integrating the equation of motion. Now, Jupiter is not really a point mass source, of course. There are multiple signals that deviate from a point mass source, including the zonal winds, the oblateness of the planet due to rotation, the tides, atmospheric structure like the red giant spot, which actually is very small compared to all these other planetary scale motion. But all these things show up in the trajectory of the spacecraft well, the trajectory is actually Doppler shift radio waves that we send from Earth and come back from the spacecraft, and they come with a Doppler shift associated with the velocity of a spacecraft. Now, one of those signals, actually the biggest, is the rotational bulge of the planet. Jupiter rotates fairly rapidly, and also is a fluid. So the hydrostatic response of that is you can see that in the radius of Jupiter when you compare the radius in the pole and the equator, there's a difference of 10%. It's a large oblateness. And that produces a gravity field expanded here in spherical harmonics. The first term is just the point source of Jupiter. Then all the other terms, the J's, zonal harmonics of gravity, describe how far Jupiter is from a point source. So we can use that data, the response of the planet from rotation or to rotation, to again create an interior model that looks something like this. This is again this quantity Z as a function of radius. How much mass of heavy stuff do we have as a function of radius? Here the axis is truncated at 20%. But again, what we see is a dilute structure, dilute core structure. There's no compact structure in the sense of something that is close to one. In fact, this is much lower than the other and extends roughly to a similar proportion of the radius, 60%. Now, this kind of modeling is not the same as ring seismology. There are actually important caveats. And one of them, maybe the main one, has to do with how well do we understand the behavior of hydrogen at high pressure, or the equation of state of hydrogen. What I'm showing you here is how the density of the planet, just normalized by something, changes as a function of pressure or as a function of depth. And all these curves represent different models to that you obtain from either a laboratory experiment or a Monte Carlo integration of equation of state, etc. There are different methods for that. What you see here is that, well, there's not an agreement really. It's that there's a few percent in different pressure levels, a few percent variation in how well we can predict the density of hydrogen. And that is enough to introduce degeneracy into the structure of the dilute core. So the model I showed you before is one of those solutions with one of those equations of state. On my judgment, one of the best, but if you use a different equation of state, you can get a less extended structure. You always get, this has been systematically done actually very recently, not included in this presentation, but very recently someone actually played with all the equations of state. You always get a diluted structure, a dilute core structure, but the extension can go from 70% of the radius to maybe 40. And that is actually very important for formation. And I will be talking about that later. But for now, we're going to keep with this model. All right, that is the current state of dilute cores in gas giant planets. That's the evidence we have for them. And now I will talk about, well, what did I do in all this new paradigm that is, racing right now? First of all, this is work I did simultaneously to the ring seismology. When Chris Mankiewicz was working on the ring seismology and Burchard was working on the rotational response of Jupiter, I was thinking about the tides. These all were things that happened in the last 3 years. And we were looking at different data sets and creating different models and etc. So it's not something that I saw that and, well, what about the tides? It was like something that happened simultaneously. And of course, we have the Earth here. There's a tidal bulge from the ocean due to the presence of the Earth. The same thing happens on Jupiter. Instead of the moon, we have way more moons. We have tens of moons. The most important are the Galilean satellites, depicted here on fresh new images. I'm not sure you can see the detail from afar, but these are actually the best resolved images we have so far from this world, from the Juno cam. This is a camera on board of Juno. Funny enough, it was a camera that was not supposed to be there because it doesn't connect to any of the science traceability matrix in the mission. But someone cleverly said, well, we cannot really go there and not have a camera on board of a spacecraft. So today we have these amazing pictures that reveal complex tectonic structures in Europa, chaotic terrain, and on Ganymede, different levels of cratering and depressions. And they certainly are preparing the stage for the exploration of this world that will happen in the next 10 years. We have the Europa Clipper and JUICE missions, both of them launching. Well, JUICE is going to launch in April, Europa Clipper next year. And from these missions, certainly we're going to change our understanding of this world and the Julian system. Now, to me, the moons are not that complex. I use them actually as a point source of mass to perturb the shape of Jupiter. And here I show you the Galilean moons with their contribution to tides normalized in the case of Io, which is the largest contributor. It's a large moon compared to the others, and also is very close. So the tidal forcing, the potential that forces the tides of Jupiter is proportional to the mass of the satellite and how far it is and size of the planet. So in those circumstances, Io is actually 1 order of magnitude larger than all the other moons. So to a first order, we can think about the tides as tides raised by Io. And the way we think about the tides is with log numbers. First of all, tides are tiny perturbations to the gravity field compared to rotation, compared to other sources, but Juno is very precise. So we can get not only one amplitude of tides, the log number at degree 2, this is the larger structure of the tide, the largest structure of a tide. We can get high degree tides. These are short wavelength tides. They have few orders of magnitude lower amplitude, but they are detectable by the spacecraft. Now, the log number is just a normalization, really, of the gravity field of the tide. The gravity field of the tide evaluated in the surface of the planet, normalized by the forcing from the satellite. And we know the forcing very well, only depends on orbital parameters as the mass of the satellite. So what is the problem then? Well, the problem is to calculate the response of Jupiter to the existence of these satellites. Now, that response can be divided into hydrostatic or equilibrium tide and dynamic. Hydrostatic tide is tides as we think about them mostly on Earth, very slow. There are no inertial effects. You can really think about it very simply as like this cup of water. If I tilt it very slowly, the level of water doesn't change much compared to the equipotential surface, that is the gravity of Earth. But if I do that very rapidly, I can splash the water due to the inertial effects. That is a little bit of what happens with dynamical tides. Another way to think about it is with the harmonic oscillator analogy. You know, an harmonic oscillator has a normal frequency of oscillation, like a building, a bridge, etc., etc. If you excite it with that frequency in particular, you can cause a resonance, and that leads to amplified motion or a resonant tide. We're going to be talking about resonant tides also in a minute, so let's just retain that concept. Now, how do we get to know the tidal response of Jupiter? Well, we have a number of equations from the material properties expressed in this one, which is again an idealization. We can use it because all this is perturbation theory. We know the equilibrium tide very well. We only need to know the dynamical part of a tide, which is unknown. And then we have conservation of momentum, tides, conserved momentum, with all the pressure and gravity terms to the right and the inertial terms to the left, including the Coriolis force, which is oftentimes approximated, particularly in all these studies of rotation on Earth take, you know, the first perturbation of Coriolis, and that's it. You cannot do that on Jupiter. Rotation is just too fast. You need to include Coriolis fully. And that oh, is there a question? I think someone needs to mute their microphone if they don't have a question. You're looking for it, or I will just mute this. So
Yeah, okay, I'll mute for that.
okay. And then conservation of mass, all the tidal motion conserves mass, and the definition of gravity that connects the gravitational potential to perturbations intensity. So we put those things together to form a system of equations that is actually fairly complicated to solve. But the results are easy to interpret. So let's jump into the results. So here we are obtaining our first retrieval from the tidal response of Jupiter from the spacecraft. That is this number, Juno observation, delta K2 is minus 5% with an error bar of 1%, 1 sigma. That means this minus 5% means that the tide in Jupiter is 5% smaller than the equilibrium tide. And we know the equilibrium tide very well. There is almost no uncertainty in that model. The reason is that the equilibrium tide is connected to the rotational response, and the rotational response is known by observation with a few orders of magnitude larger in amplitude. So you can create a model that reproduces the gravitational response, and the model doesn't even need to be right. It only needs to match the gravitational response and then use that model to forward model the equilibrium tide, and you get what is the amplitude of the equilibrium tide. There are technical elements there that are quite complicated, but the message is the equilibrium tide is very well known. The error bars in the prediction are 0.00%. So this error bar is just an error bar from the observation, right? From the mission. Now, the first thing we can do, well, and we take this observation and we put it in a plot of change of the equilibrium tide as a function of frequency. And this is, of course, the observation associated to the frequency of Io. We have the frequencies of the other Galilean satellites, but we don't have data for those. Tides are much smaller in those cases. So the first thing we can do to try to understand this number is think about the harmonic oscillator analogy. In the harmonic oscillator, we have two frequencies. One, the frequency of excitation of the satellite, that is just the orbital parameters of the satellite. How long does it take the satellite to go around, and how fast is the planet spinning? So that's the excitation frequency. And the other is the fundamental frequency of the planet. How is the planet oscillating? That is the normal mode of a planet. And we know that actually very well. And we know that that mode is actually not very dependent on the interior structure, other than saying it's hydrogen and helium. So we can use reasonable numbers there and get something like plus 30%. Very off, different sign even from the Juno observation. It's not an harmonic oscillator. Actually, the harmonic oscillator will never give you a negative value because the excitation is low frequency compared to the oscillation of the planet. The planet oscillates with a period that is much longer. So if you think again, this resonant plot of the harmonic oscillator, the peak is very to the right. Your excitation is always going to be higher than 0 in terms of amplitude. Never negative. Okay, so the harmonic oscillator doesn't work. And this was actually the state of the art when I began working on dynamical tides. I remember the day I walked into Dave's office, that was my PhD advisor. He began talking about tides. I'm like, oh, this is interesting. It was, a young PhD student. And then I asked, well, this is great. What is the literature on this topic? And he points me out to a Russian paper from the Soviet Union, 1984. That was, it was luckily translated to English, but it was the only thing that was available at the time. They had actually a more complicated model. We proved at the beginning that what they did was equivalent to an harmonic oscillator. Now, the next thing you can do in terms of additional complexity is uniform density. Of course, Jupiter is not uniform density. It's highly compressible, but this is convenient because can be obtained just analytically out of the equations. And this solution actually includes the full effect of Coriolis, so you can actually get the dynamical tide of something that is uniform density that is rotating rapidly, and that is minus 8% when you plug in, the values for the radius of Jupiter, gravity of Jupiter, the rotation of Jupiter, and the frequency of the excitation of the tide. That is closer to the observation, but not quite yet. We can do much better than that if we say we solve these system of equations I showed you before, which are fairly complicated. There's coupling involved. You need to use a spectral method. It's actually fairly complicated to get a very simple number, but the simple number is in agreement, much closer to the observation. And that's it. We see the first evidence of dynamical tides in a gas giant planet. So we have a first in that sense. It's interesting. And this is, the first evidence of a phenomenon that is used typically to explain the orbits of the satellites. And we need these dynamical tides to create dissipation, to move them away, in the case of Jupiter, and to create the Laplacian resonance. On the disappointing side, we don't learn anything about the interior structure, because when we move from very radically different model structures, uniform density and highly compressible hydrogen, we can even explain the data with 3 sigma errors, right, with any of these two models. So now if we introduce a small perturbation, say the core of the planet, we're going to land maybe somewhere in between, but we're not going to learn anything from this. Now, that's it. We're done. Well, not really. We luckily, as I mentioned before, have additional data. This is the other tide, much smaller in amplitude relatively to K2, K42, and shorter length scales. Entirely independent in terms of the modes of the planet that are associated to this tide. So it's a new opportunity to do some modeling. Now here I'm playing the same game, the same plot I explained to you before. We can change from the equilibrium tide. Now the equilibrium tide is K4, a different tide. It's a function of frequency with the data point for Io obtained from Juno. And here we can actually have 2 compressible models with a different structure for the core. And one of them, we have something compact that is similar to the traditional core, not exactly that, but the idea is that we concentrate all the mass near the center. And then we have a diluted core where the mass is distributed more widely and broadly along the radius. And these 2 different models have different normal modes. And in the case of the extended structure, we can actually perturb the geometry of the core, find a normal mode that is resonant with the frequency of Io, and therefore produces an enhanced gravity signal. The waves involved in this resonance are internal gravity waves that are trapped in the core and are excited by tides. Now, the caveat of this story is the following. You have infinite modes in a dilute core like this one. And you can, in principle, modify the structure of the core to make any of those modes match the frequency of Io. Now, I say in principle because in practice that is not true. Some of those modes will prefer to be excited by tides, will be more favorable to be excited by tides, and some of those are not. So what I have done here is to take the mode that is most easily excited by tides and say, what is the geometry of the core that produces a frequency for that mode that matches Io. So when I say many and infinite modes, what I'm talking about, if you are familiar with seismology, is modes with different order or radial degree. So you have infinite overtones, and they go, they cover the whole spectrum. But the high degree overtones, high order overtones, have multiple crosses by zero, and that actually couples very badly and poorly to tides, which is a forcing that has zero crossings on zero. Okay, these waves have been observed in a different area of planet Jupiter. This is an image from Galileo in the mid-90s, when captured the impact of comet Lavi. There was a comet that just crashed against Jupiter and created waves, ripples that propagated in the atmosphere and were later identified to be internal gravity waves propagated in the stratosphere. Now, this is a very different area to what I'm talking about. This is superficial. The density here is almost zero and produces almost no tides. The core is actually in a region in the planet where density is much higher, order of unity or larger. And so the displacement that those waves produce actually change the amplitude of the tides. Okay. That is mainly it in terms of how do we relate the structure of the planet to an observation of the tides. But there is a problem. And I will tell you what the problem is, and I will offer you a solution. What is the problem? That we are highly tuning the interior structure to match the frequency of Io. Can we do that? Well, we have different processes associated to evolution and that are a challenge that we need to address. First of all, we think about the system at a different initial state to what we observe today. We might think that Io was closer in the past. The reason is that Io is migrating outward because Jupiter rotates faster than the orbital motion of the satellite. In that circumstances, you will always have a tide pushing the satellite outward. And so the frequency of the tide is changing in billions of times, billions of years. Furthermore, and independently, seemingly, there is convection in the interior of the planet in different forms, overturning convection or double diffusive convection, that is changing the structure of the core. So the core is changing frequency as well. These two things don't need to be connected in principle, but they can. And the way they can be connected is with the idea of resonant locking. This is an idea that has been applied to the migration of planets and the migration of binary stars. In this scenario, what I'm going to do now is to propose a self-consistent scenario that allows us to think, well, there is a situation with uncertainties, but a situation that leads to predictions, so we can test it. And in this situation, we can invoke this resonance, not as a coincidence of two frequencies being equal, just in this instant that we are observing. We are observing 3 years of something that has a history of 5 billion years. So we are not observing a coincidence in terms of two frequencies matching, but we are observing an evolved state, a state that has gone through an evolutionary process, and we're seeing the final outcome of that evolution. So what do we have here in order for that evolution to lead to this state of evolved, to this evolved state? First of all, what we have here is time in billions of years as a function of frequency, and we have two lines that represent the frequency of the core and the frequency of the tides. In light blue, you have the core. So the core must be evolving to a high frequency so that you have convergence with something that is evolving with tides, which are also evolving to high frequency due to the expansion of the orbit. So this is actually a requirement. It doesn't need to be like that, but you need that in order to have this scenario to be self-consistent. Okay, and so this is a prediction in the sense that you would have this scenario if the core is evolving in this way. At some point, these two frequencies are going to intersect, right? And instead of the orbit continuing independently like a straight line like that, the migration of the orbit will adjust to the migration of the core. The two things will continue evolving in synchrony, because what you attain here at the resonant onset is a point of stable equilibrium. The details of that are numerous, but I will just describe what are the consequences to have this point of stable equilibrium occurring. And it has to do with dissipation. How dissipation happens, or how the orbital migration happens, has to do with this mechanism right here. This is the satellite, and this is the planet Jupiter. So you have Jupiter perturbed by the tide. The tide is not aligned with the position of the satellite, and that is because of dissipation. There's a time lag for the bulge to align with the satellite. So this is rotating in that direction, right? And this misalignment creates a torque that pushes things outward. Now, the intensity of the torque depends on the amplitude of the tide, which is the log number, and the inverse amplitude of dissipation, which is the quality factor of the tide, right? So we need to have two things. First of all, Q needs to be small enough, so this thing is enough away from the no dissipation case, so we get just because of the resonance, right? The Q you obtained in the resonance should be small enough so that this torque can push the satellite at a faster pace once you hit the resonance, right? So Q should be small enough to do that, right? And we can do an order of magnitude calculation of how do we think the satellite migrates here, and what do we need for Q to be in order to cause a similar migration rate just due to the resonance. And the second thing that you require is that the log number needs to be large enough. So we explained the observation from Juno. When you have a very low Q, you damp the waves, you go in the risk of making this log number too small and not be detectable by the spacecraft. So there's again two competing things. Q cannot be too low in order to have the observed thing. This leads to an estimate of 1,000, right? A Q of 1,000. It's a simple modeling and order of magnitude calculation, just trying to see whether this scenario is plausible. And with this scenario, we can provide an explanation in the sense of, well, we may have this resonant configuration as the outcome of tidal evolution. Q of 1,000 is low for gas giant planets, maybe not low for the Earth, but it's low for hydrogen. When you have hydrogen, it's hard to have a Q of that magnitude. And actually, theories struggle to produce low Qs. Now, we have observations in a different system. This is Saturn and Titan, where from measurements of the velocity at which Titan is migrating, one can estimate that the Q in Titan is 100, an order of magnitude lower than this other model. So it might be that the theory really is not representing what we observe. So that's the end of the story. Okay. Now, just to review some of the conclusions, what have we done? What have we learned from the tides uniquely? So first of all, we have, for the first time, an observation of dynamical tides. The first on that. It doesn't tell you what the structure of a planet is, but it tells you that you have this process and validates a lot of uncertainties that we had before regarding how planets migrate. Second of all, there is one log number that requires a resonance that can be obtained with certain geometry of the core. The solution is not unique in the sense there is more than one geometry that can obtain that resonance, but there are reasons to think that the structure that we choose is this dilute core extending far out, similar to the gravity observation from the rotation. This is the preferred model. There are reasons to think that. Okay. And then finally, well, there is things that need to be worked out, like theory of dissipation in gas giant planets is something that needs to be developed eventually. And in terms of observations, we have a set of predictions. The first prediction is very testable in the sense of it's just, if we look at Jupiter and we find a way to observe the normal modes, a spectrum of normal modes, what we are predicting is that Jupiter will have a core mode, a internal gravity wave mode at the frequency of Io. It's a clear prediction. If we are right, that mode should be there. If we're wrong, the spectrum will not show that. Now, to summarize, a short comparison of this dilute core problem and how does impact are ideas of planet formation. So on the left, we have Saturn, right, Jupiter. This is from rotational gravity, and this is from the tidal gravity. These two images are very similar, and both of them favor something that reaches 60 or 70% of the radius. On the contrary, on Jupiter, we also have 60% of the radius, but remember that Jupiter, Saturn, sorry, is smaller. So when we convert this into mass of a planet, because if we think about the planet forming like an onion, right, from with different layers from the center to the outer layers, we need to think about mass, right? So when we think about the extension of the core of Saturn, it's this 70 masses, 70 Earth masses are like 60% here, right? In the case of Jupiter, there's a range that goes from 60 to 150. 150 corresponds to this very well extended force. But if you have a different equation of state, you can reach something that is 60%. Now that is interesting because it signals a common origin for Saturn and Jupiter in the sense that these two planets formed maybe a core, like an embryo, like in this phase one, I show you of planet formation. Maybe then you get to form something like a dilute core on top of this compact core, and that structure is 70 or 60 Earth masses. Now Jupiter is different from Saturn only because you then accreted gas on top of it, and nothing like related to the structure of the core. So that signals to a common origin. Now we have the additional evidence of tides, and this model that is the best equation of state that signals maybe that the extension of the dilute core is actually not the same as in the case of Saturn. So that common origin is defied. So we have these two alternative situations, and we don't have an answer to that. So it's one of the things that we're going to try to be solving in the future, the extension of the dilute core, rather than just the existence of it. Okay. In terms of the total amount of mass, again, it's the same. This M star is the total amount of core material. It's the same number in the case of Jupiter and Saturn, and this is in agreement with this very simple idea about the radius of the planet. Right? You predict the same numbers just by looking at the radius of the planet, and these are numbers that you get with very complicated models. Okay, a final thought related to evolution. What I'm showing you here is what happens to a Gaussian planet. Well, not really a Gaussian planet. These are actually very simplified models, just 2D. This is a gradient in temperature, cold and warm. This is a gradient in composition, light material over heavy material. And things are getting pulled off from the top. So there's a heat flux in this boundary, and that heat flux induces convective currents. All these things you see here is convection, vigorous convection, really, that is capable of penetrating into this compositional gradients, driving material, and cause mixing. This is to highlight the point that if you have something like a Gaussian planet that is cooling off from the surface, and you let an infinite time to happen, you lose the core. Things get mixed eventually to an homogeneous composition and an homogeneous temperature. It's just a matter of time scales, right? Now, there's models from Rafa Fuentes. These are suggesting that even in the timescales of Jupiter, with the I-dimensional parameters that correspond to Jupiter, you may have a strong case for full mixing. This is important because it's at odds with the idea of an extended dilute core. Now, these models, again, are very simple, just 2D boxes. There's no Coriolis, there's no magnetic field, and we know that those things impose constraints on how convection actually happens. So you cannot have really currents doing whatever they want, that there's a constraint given by rotation, and those things actually need to be investigated in the future. So that is from the theoretical side, another thing to have in mind. I'm running out of time, so I will go very fast about the future. The future is, well, Juno is still there collecting data, and it will be until at least 2025. Unfortunately, most likely the extension of the core will not be solved by Juno. We need a different strategy to observe the interior of a planet, and that is, at some point, gravity has a fundamental limitation. It's sensitive to the outer layers. When you want to look at what is going on very deep, doesn't matter if you stack infinite data, it's not going to give you more information. So an alternative is Earth-based astronomy from already 2 decades, or a decade at least. There has been efforts to get the spectrum of Jupiter from looking at the light of Jupiter, comes from Jupiter. And if Jupiter oscillates, it's changing its shape. So you might be, in theory, able to see variations in the light curve of Jupiter. Now, so far, the efforts have been unsuccessful. This is the spectrum of noise of Jupiter, and that should be showing the spectrum of normal modes. And the problem is that you really need very, very long times of observation to get below the nose level. And observations of telescopes are very scarce. No one will give you a month of, say, Hubble or any big telescope to observe just one target. So there are efforts, and this is going to continue probably. Teams around the world are trying to get this kind of observation. We'll see what happens. If we want to dream further, this dream of planetary exploration, here is Europa Lander, a concept for the exploration of Europa. Well, we have a system of internal moons. It is heavily radiated, so to be there is actually very hard. But if we were able to put a gravimeter or a seismometer and any of those tiny moons, we might get a signal from the oscillations of Jupiter. And finally, just to close, this is what I am doing right now on my postdoc. I'm working on, well, these bodies, icy moons that have global oceans below the ice shelves. We know about the existence of these oceans from magnetic data, and in some cases from tidal data as well. We don't know very much about the properties of these oceans, but we know that those properties are important for habitability. Basic things such as what is the salinity of the ocean can help us to constrain whether the ocean is in circulation or what pattern of circulation do we have, and how heat and potential chemical tracers are being distributed in the ocean. So what I'm doing actually is to anticipate the arrival of these 2 missions that will be collecting gravity data on these objects and seeing how we can connect, again, the tracking of the motion of a spacecraft to internal properties of the ocean, for example, a stratification from salinity or stratification from other compounds, and doesn't need to be salts necessarily. That's it. And I had a great time talking to you today. I hope you also enjoyed this line of research, and I'll be happy to answer any questions or hear any comments you may have.
Thank you, Ben. A great talk. We would like to first invite questions from students.
I have a question. So you said on Saturn, you're doing ring seismology, and that wasn't a possibility on Jupiter. What's the reason for that? Because Jupiter also has rings, it's small.
Yeah, they're not massive enough and they're too faint. And so you don't really get the chance of observing waves traveling there. Also, you have a problem to create the resonances themselves due to the low mass of the ring. But yeah, you're right. There is a ring, but it's just too faint. We are lucky that Saturn has a ring, really. Without that, we would be blind on the interstellar planets. It's a natural constant, really. Now, it's a good question, and sorry, I will elaborate on this on a different topic. So Saturn is smaller than Jupiter, and as a consequence of that, you have deeper winds. And that is because the electrical conductivity of hydrogen doesn't raise this until you're very deep into Saturn. The electrical conductivity of hydrogen actually allows you to damp the amplitude of the winds. So bottom line is you have strong winds on Saturn that penetrate very deep into the planet. That makes seismology very hard. The winds perturb in normal modes, make the modeling very hard. You don't know exactly what the structure of the winds is. So your modes are always perturbed in terms of uncertainties when you do the modeling. On the contrary, in Jupiter, where we don't have those deep winds, perfect for seismology, we don't have the rings. That's what it's a kind of irony. Okay.
Thank you for the talk. That was great. I'm curious, I was curious earlier in your talk about, what intuition or observation you would have about changes in the core or the dilution of the core over time. And maybe you sort of answered that with the convection at the end. I was wondering whether, if you have this theoretical idea that the convection is mixing and diluting the core over time, is that something we could ever observe? What time scale is that convection happening?
Yeah, it is bounded to be slow, like geological times, and so I don't venture to tell you exactly how fast it is, but if you observe a dilute core today, yeah, it's something that is changing on the scale of billions of years, right? That doesn't mean that convection has that time scale. It's just that is a time scale that erosion is happening, right? And erosion depends not only on convection, but also on the strength of the chemical gradient. So what happens really is that you have these two areas, convection on the top, at the bottom, you have a stratification with this chemical gradient. And if they were entirely separated, that would be great. The thing would be stable very long. You would only have diffusion, really, and material diffusing from the stratified layer into the convective layer, and then joining the currents. The problem is that the currents overshoot. So they penetrate into the layer of the core, and they drag material outward. That could be really fast or it could be really slow, depending on the structure of the convection, which is not known. It's a huge uncertainty, the structure of the convection, and depending on the strength of the stratifications. And magnetic, so everything's coupled. And in problems like this, unfortunately, you cannot go about the Earth with rotation is just a perturbation over something that is static. You need to address things fully. Mathematics are really complicated.
Thank you.
Kind of a follow-up question on that. So you mentioned Jupiter's core can be diluted over time to good, and if you compare that to Earth, why doesn't Earth's core go away? What's the fundamental difference between these two candidates?
Well, this fundamental. There are many differences. I'm trying to think which one would be the most illustrative. Well, the time scale of convection is certainly different, right? On Earth compared to Jupiter. On Earth, the time scale of convection is slow, but not that slow.
So the thing is because Earth's convection, or Earth's mantle's convection is not vigorous enough to just take away from material.
Also, well, yeah, also you have, well, that's one thing. I'm just trying to think on the fly, what is the most important thing? You also have iron being much heavier than silicates. So what you're doing on Earth is you would need a convective current capable of being strong. So you have two effects, right? One of them is the chemical stratification, silicates over hydrogen, so light material over heavy material. And then you have convection because of a thermal gradient. You have hot stuff at the bottom, cold stuff at the top, right? Those two things compete with each other, okay? And so the one that is stronger will win. And so if, for example, if the thermal gradient is stronger than the chemical gradient, you can have convection and dragging things up, right? So in the case of, the core mantle binary, you would need a temperature gradient capable of lifting iron and make it neutrally buoyant while, suspended on the mantle, and that's really hard.
That's the thing is the density contrast that is playing a main role here.
Another way to say it's just density contrast. You say very strongly. Density contrast, yes.
Okay. Sorry, I probably didn't follow. What is the Jupiter's core made of?
So we don't know the exact composition, and so in astronomy, the difference of Earth, when we don't know exact composition, we say we have buzzwords like rocks and heavy elements or metallicity. So it's just rocks, silicates mostly. It's not hydrogen. It's not helium. Sorry?
It's not iron.
Oh, there is iron, yes.
Oh, there is.
Surely, yeah, but iron, so the way you can think about this, and really probably the best way is just looking at the cosmic evidence of the abundance of elements in the nearby galaxy. So you look at different stars, you can identify the amounts of iron compared to oxygen and helium. There's a table, right, of all these abundances. You can use that to infer, well, how much iron can I have on Jupiter? It's not like on Earth where you have, this a high concentration of iron.
But don't we know the moment of inertia?
Oh, we do, yeah. So, but the moment of inertia helps, but it's not enough to, it's not known well enough to just from that get the structure of the core. But yeah, we do know it. And the problem is related to the pole. There's polar wonder, the pole is moving, and that actually complicates the estimation of the moment of inertia from a spacecraft. So there are uncertainties on the moment of inertia that are associated to that migration of the pole. So we don't know how the pole is moving. If we knew that, it would be much easier. This model is actually very widely when you change the model for the pole.
Any more questions from the general audience?
By the way, the moment of inertia is related to the gravity as well. Now you can think about this J2, J4, J6. They're related to the moment of inertia. They're not entirely correlated, but they're not entirely independent either. So when we do the analysis, to the rotational effect, we're basically doing that and looking at the different structure of a moment of inertia, but with additional information. So, yeah. Now, the moment of inertia is nicer in the sense that it penetrates deeper. When you look at the sensitivity of a moment of inertia as a function of depth, you get a little bit deeper than the rotation. In the J's, as you go to higher order, things become only sensitive to the very shallow layers. So you can use it together, but even when you do that, yeah, you don't solve the problem of the extension of the core.
Okay, so the internal structure of Jupiter has been evolving. Its density profile has been evolving from something less dilute to more dilute. Is that right? Is that the prediction based on convection?
Yes.
So today it's more dilute than it was in its earlier.
Well, the prediction of what? Of my story? The prediction of my story is that things are shrinking. Okay, so that's what I need to make the resonance stable. But we don't
Things are
know.
shrinking.
Yeah,
It's getting less dilute.
yeah, that's what you need to make the resonance stable over, say, 1 billion years, right? But that doesn't mean that observation required by the resonance is necessarily consistent with mixing, which is an entirely different beast with huge complications. And what I showed you here is just a glimpse of that very recent work. You saw the date is 2022. So I think people are just starting to put additional machinery and technology into this to get convection on 3D with rotation, et cetera, et cetera. So when you ask me whether the prediction from mixing models is one or the other, I can't tell you an answer because we don't know.
Okay, so the density profile that you showed is something that could be inferred for a good amount of Jupiter's history.
Well, if you know the evolution, you can do it, yeah. You know the evolution very well. But again, you go back to knowing how things are evolving. So at this moment, the state of research on this is, well, let's think about the formation, ignore evolution entirely. Or let's think about this initial state and see how it happens and how does it evolve over time. The two things are not connected. There's no self-consistent framework to analyze this problem. The answer is natural. We didn't have data until 2 years ago. So things are starting to move forward theoretically speaking, but they're still slow. And the data is actually not even well known. The mission is still going on. So, things need to get assimilated by the community, and all these things are going to be eventually done. So far, a lot of the answers that are basic questions for Earth are not known today in the case of Jupiter, which is not simply another planet, as I said, rotation and all that.
So the current tidal dynamical tides, like the K42 that you're observing, that's creating the resonance to lock in where Io is at.
Yeah.
But so you can infer that is based on its current, it's having that tide, you can infer that tide existing, that its internal structure exists in a way that it can produce the tide that then locked in Io, but Io is migrating previous to that.
Yeah.
Right, all the Galilean satellites migrating for some time. Until they've reached these resonances.
Yeah, they were migrating at different rates,
Yeah,
at a slower rate.
but my question is, that's tied to the evolution of the interior density profile,
Correct.
to where they got locked in.
Yes.
Uh,
And that evolution has to be a density profile that, well, it's not only density profile, right? It's also, it's mostly the distribution of heavy elements in the chemical gradient. So that distribution is. I understand your question. I'm trying to answer this concisely. One sec. I think I understand your question. So this is not a density profile. This is just chemical gradient, but it's connected to the density profile. Okay. So in order to have this resonance locked in for say 1 billion years, you need to have this core shrinking. So in the past should have been a little bit more extended, and the thing is shrinking. So you can say from the tides, well, we need a core that is shrinking. How strong is that claim? I propose this idea, and I think it should be tested.
Okay.
Right? And so, you know, it's an observation from tides, and it has a self-consistent model. But again, the uncertainties are big, and the way to analyze this kind of research is we have a suggestion that things work this way. We need to test them rather than to say this is how things are working. Okay. And one way to test it is this models I was talking about before, right? We need to do this mixing model, including all the complexities, et cetera, and see what happens and see if these things are consistent or not. Great question.
So, on one of your slides, I think, is talking about how, the uncertainty in the equation of state meant, that, you couldn't, or it, limited the amount that you could learn from the bulge. So, if, you knew the equation of state a lot better, how much would that help? And are there any prospects that, we will learn a lot better?
That's a great question. You anticipated the future. That's something that actually people are trying to do right now. I think there are conversations within the mission team, the science team, with people on the high pressure physics community to run these experiments. They can be done. They're not at a crazy level of pressure that has not been done before. Actually, it's exactly the opposite. The high pressure physics community, they overshoot. They're just trying to get the higher pressure they can. They are way beyond the pressure that you see at the center of Jupiter, say. So they will have to adjust their experiments, the things they do typically, write proposals, and try to get better laboratory experiments that can be later translated into better equation of state. So when we look at the data that goes into this is a slide you're talking about, I think, into building these curves, right? Especially this area. This area is of high importance, and this is where you have the larger differences among models. This area has a few points, really. So you're right. If you had more experimental points of the adiabat, say at this pressure, what is the density that you get in this tiny samples? These are tiny things. You get a tiny sample of hydrogen, and you can do it either with diamond anvil or with shockwave experiments, and then you can reach this temperature and pressure in the adiabat of Jupiter. And if you get a few more points there, you can improve the equation of state, and that will help. In which regard? It will help to constrain this range. I went over this range right here, right? We have a range for the extension, right? So knowing more from experiments on hydrogen on Earth, we don't need a new space mission. We can constrain this range to its shorter value. Not sure if it will be good enough to say something like we can say on Jupiter. On Saturn, this is actually very precise on Saturn, okay? Seismology is really good compared to gravity. But it'll get smaller, the range will get smaller.
So when you compare your observations to like the original observations that have been going on in recent years on all past ones?
Oh, these are ab initio. These equations of state. These are some of these are ab initio. Okay. So these are the equations. So I actually so I don't use this directly. I use it only indirectly. The reason is that the tide is small compared to the gravity field of the planet. I can use linear perturbation theory. That's the simplest perturbation theory you can use. And that allows you to not know, in order to capture the dynamical effect, you don't need to know the base level. It's just a percentage deviation from some value, right? So all the theory I developed is just a change, a small change from that. So I am not dependent on this level of uncertainty, frankly, with the things I do. So that's good. It's a positive thing compared to rotational bulge. There are other kind of uncertainties in the analysis I did, but I'm not dependent on this problem. And I have where I am dependent, but only indirectly, is on the amplitude of the equilibrium tide. But there, it doesn't matter really. With any of these things, you get the same amplitude for the equilibrium tide, and the reasons are the J's. So you have an observation that is the rotational bulge. J is some number. Then you can create models that will fit that number. The models can be different, right? They can have different structures, different entropy, different cores, right? They can be wildly different, very different planets even. But this J2, right? They all fit the J2 in the same degree. Now you can use any of those models and forward model the equilibrium tide. That is another value that is correlated with this one, and you will get always the same equilibrium tide. And that is because you're tied to the observation of J2. So in that sense, I'm not sensitive to this in any way. Yep. But I needed to get the equilibrium tide, but I can use any of it.
Okay, due to the time limit, we will end the Q&A session. If you have any more questions, please feel free to reach out to them directly. So let's thank them again for the excellent conference.